In continuation with the previous topic on conducting polymers, as I said, we are going to look at what is spinless charge carriers. So for that, we will be learning about polarons, bipolarons, and then you will have an idea. So starting with distortion energy. So what do you mean by distortion energy? You could see on the diagram on right hand side at the lower corner you have something called E suffix dis. So that is the distortion energy. So in organic molecules, normally you see that the equilibrium geometry in the ionized state, when you ionize them, already I told you about ionization in the previous topic. When you ionize them, they have an equilibrium geometry which is different from that of the ground state. So they will have to get relaxed a bit. That is EREL, relaxation energy. And the difference between uh, EIPV to, that is E1PV to E1PD, that is from the undisturbed one, undoped one to the one which is under distortion energy now. You could see there is some difference. You call that as delta E, the energy difference. Fine. Having this in mind, we will move on to HOMO-LUMO shift. So you would have studied about conduction band and valence band in physics, that is in semiconductor physics. Similar to that, when you talk about organic molecules, you say HOMO, which is highest occupied molecular orbital, that is your valence band, and LUMO, which is lowest unoccupied molecular orbital, which is nothing but your conduction band. So this is how it looks actually. So if you consider one energy level of the molecule, initially when there is no dopant at all, no doping, as it is, the material is in its original position, you could see the band gap. How much is the difference between the top of the filled one to the Fermi level. Then slowly when you have some distortion to it, and then you could see there is the first ionized state and the value also varies, right? That is, the bands come closer to each other. That's a shift in the conduction band because of the relaxation energy, E E suffix REL from the previous slide, and there is a shift in the valence band, which is because of the distortion energy. So in continuation with this, we could see what is polaron and why it is formed. So what happens actually is when you take oxidation. So you remember when we said about N and P type doping in semiconductors, it is like the redox, that is oxidation and reduction in polymers. Fine. So take the case of oxidation, that is removal of an electron from the chain. You are going to remove an electron from the chain. So the electron will have to leave the valence band and it has to be shifted up. So this value of delta E also will show some change. Now, this if this value is larger than the energy needed for distortion, E suffix dis, necessary to distort the lattice, there will be some locally available charge, which you call it as charge localization. We then obtain the formation of what is called as polaron. So what do you mean by polaron? In chemical terminology, polaron means radical spin, radical ion, that is half spin, that is associated with lattice distortion and the presence of localized electronic states in the gap, and that which is referred to as the polaron states. Okay. So in the case of polaron formation, you could see that the valence band remains full, whereas the conduction band is empty. Look at the diagram B, figure B. The valence band remains full and the conduction band is empty. And there is no appearance of metallic character. Okay. So this is what we see in the formation of a polaron here. Now, bipolaron. So further, if you oxidize the same thing, so when a second electron is removed, initially to form a polaron, only one electron was removed, and we saw the energy levels appearing in between the conduction and valence band. So now when you remove the second electron, you call it as, two things can happen. You can remove the second electron from a polaron itself, then you call it as a bipolaron. or you can remove it from anywhere else. In that case, you will have two polarons being formed. We'll see that in the next diagram. Okay, this bipolaron is quite interesting. As I was talking about the superconducting nature in the previous two slides, here you could see this bipolaron can be compared to Cooper pairs in BCS theory of superconductivity. That is, the electrons join together as a pair, which is really not feasible, right? And that is possible here in bipolar. So this, since the lattice relaxation around the two charges is stronger than only one, this bipolaron distortion is larger compared to that of the distortion for polaron. Or also, there will be electronic states appearing in the gap for bipolaron, which are further away from the band edges. So for a polaron, they are little away from band edge. When you have a bipolaron, they'll be even more away. So that would be an advantage also. So that is seen in the diagram here. The figure A shows the formation of two polarons. And you see figure B, which is a bipolaron, where you could see the band edges, the discrete levels far away from the band edges. Okay, so the bipolar is, so if you see in the case of p-type or n-type doping, it is the same actually. In case of p-type or n-type, you have the bipolaron levels in the gap which are empty or which are fully occupied. So thus you can see either it will be empty or fully occupied. Overall, it is spinless. If it is a single electron, yes. Here it is going to be spinless. That is why they are called as spinless charge carriers. And these are the bipolarons, which mean they are spinless. Okay. What happens because of the presence of bipolarons on a polymer? You can see two transitions can happen. Okay. From the valence band, it can go to one of the lower bipolaron level, and then again the next transition can be from the valence band to the upper bipolaron level. So this is an advantage. So here is an example. You could see this is a polymer which is called polythiophene. So initially you have the homolumo of the undoped polymer, right? And then you make it undergo either oxidation or reduction. That is accordingly whether you want to make it p-type or n-type, right? First time you do an oxidation, you could see something happening, and then again you go for oxidation, you end up with the formation of bipolaron there, and when you go for reduction, you end up with the n-type material, whatever you want. So the doping process generates positive or negative polarons or bipolarons. That is possible here. And let us look at one more example where you could see the formation of bands. So here the example is PPY, polypyrrole. Polypyrrole has a wide band gap of around 3.6 electron volt. Initially, when you oxidize it, you will see a pi electron is removed. You could see in the diagram a pi electron will be removed and it forms a polaron. So because of that, you will have two localized electronic levels in the band gap. Again, when you further oxidize it, you will have a second polaron being formed, right? So you will have doubly charged bipolaron. Then what you see is further oxidation. So when you further oxidize it, then you will be ending up with the formation of bipolaronic bands. You could see the band there. Like we have marked it as 0.3 and 0.4, right? So overall, what happens because of this is there is a decrease in the energy gap. Initially, when it was the undoped, the acetous, the polymer was undoped, the band gap was 3.16 electron volt. Finally, after the formation of polaron, bipolaron, and then fully doped state, where you had the bipolaronic bands in figure D, you could see that the band gap is reduced to 1.4 electron volt. Thus, from an insulating character to a conducting material. So this really helps in the formation of conducting polymers, inherently conducting polymers. Thank you.